This is going to be episode 4 of the subject of differential equations, and in this particular episode I want to deal with what are called first order linear differential equations. The general form is written here in red, and it reads as dy dx plus y times p of x equals q of x, where p and q are functions of the independent variable x. Now, let's just look at the left-hand side of that, which is dy dx plus y times p of x, and equate it to 0. That is known as the homogeneous equation of the differential equation. Okay, so in this particular equation, the variables can be separated so that we get dy over y equals minus p of x dx, and on integrating we quite easily get log to base ey equals minus the integral of p of x dx plus log to base e of k, which is our arbitrary constant. And so, raising both sides exponentially, we get y equals ke to the minus integral p of x dx, and then multiplying both sides by the exponential part, we get y equals e to the integral p of x dx equals k. Now, if we take that expression y equals integral p of x dx and differentiate it with respect to x, it will give us y times p of x e to the integral p of x dx plus dy dx e to the integral p of x dx, and taking the exponential factor out, we get e to the p of x dx, and in brackets dy dx plus y times p of x. So multiplying the left-hand side of the original equation by this quantity e to the integral p of x dx gives us an expression whose integral is y e to the p of x dx. So to solve the original equations, all we have to do is multiply both sides by e to the integral p of x dx, which is called the integrating factor, and the solution will be y equals integral p of x dx equals the integral of the right-hand side of the original equation, which is q of x, multiplied by e to the integral p of x dx, and then plus your c. Okay? And I've said the only likely difficulty you're going to encounter from now on will be if the integration is a bit awkward. But in the following examples, we shall try and keep things reasonably simple. So I'm going to do 5 examples here. It might be a good idea if after the first one you tried to do the rest on your own and then came back and checked your working afterwards. But it doesn't matter. If you want to stick with me for all 5 examples, then that's fine. Okay, so here goes with the first one. Dy dx plus 2y equals x squared. Now the integrating factor will be e to the integral of 2 dx, which is e to the power 2x. And then our solution will be ye to the 2x equals the integral of x squared e to the 2x dx. Now this is just a routine exercise in integration by parts, and what you will end up with then, on the left-hand side, y equals 2x, and on the right-hand side, e to the power 2x, and in brackets x squared over 2 minus x over 2 plus 1 upon 4 plus your obligatory constant c. Or just multiplying up by 4 and multiplying both sides by e to the minus 2x, will give us 4y equals 2x squared minus 2x plus 1 plus c, the constant, times e to the power of minus 2x. So that deals with the first one. Second one is fairly similar. So read it out. dy dx plus y cos x equals 2x times e to the power minus sine x. The integrating factor here will be e to the integral cos of x dx, which is e to the sine x. And then multiplying through by that, we'll get y equals y to the e, I'll start again, y e to the power sine x equals integral of 2x dx, which is simply x squared plus the constant c, and then rewriting that, you get y equals c plus x squared times e to the minus sine x. That should have been simple enough to follow. Okay, we'll go on to the number 3. X dy plus y dx equals x sine squared x dx. Dividing through by dx, we'll get dy dx plus y over x equals sine squared x, which I've written in a different form because of the integration in mind, which is 1 minus cos 2x over 2. The integrating factor will be e to the power 1 over x dx, which is e to the log x, which is, of course, simply x. So now yx equals 1/2 of x times the right-hand side, which is 1 minus cos 2x dx, and that equals 1/2 of x dx minus 1/2 of x times cos 2x integrated. And the first integral is quite easily x squared over 4, and the second one, again, is a fairly routine integral, and should come out to minus 1 over 4 x sine 2x minus 1 upon 8 cos 2x plus the obligatory constant c. And finally, just multiplying up by 8, we'll get 8xy equals 2x squared minus 2x sine 2x minus cos 2x plus c. So that does the third question. We'll now go on to the fourth. I'll just check that last one again. Yeah, that's all right. Okay. We'll go on to question number 4, which is dy plus 3y dx equals sine 2x dx. And then dividing through by dx, we get dy over dx plus 3y equals sine of 2x. The integrating factor will be e to the integral 3 dx, which is e to the power 3x. And then y to the power e to the 3x equals the integral of e to the power 3x times sine 2x dx, which again is a routine exercise in integration by parts. And we will then get on the following line, y equals e to the power 3x equals e to the power 3x divided by 13, bracket 3 sine 2x minus 2 cos 2x plus the obligatory constant c. And then finally, tidying that up a little bit, we get 13y equals 3 sine 2x minus 2 cos 2x plus ce to the power minus 3x. So that deals with question 4. Just one remaining. And this one reads as dy dx plus y equals sine x plus cos x. The integrating factor will be e to the integral 1 dx, which is just e to the x. And so y e to the x will be the integral of e to the x sine x dx plus the integral e to the x cos x dx. I've labeled these two integrals as I and j, and looking at the second one, j, and integrating by parts, you'll get the first times the integral of the second, which is e to the x times sine x, minus the integral of the first differentiated, which is e to the x, times the second integrated, which is sine x dx, which is e to the x sine x minus the integral which I've called I. So from that you quite easily get I plus j equals e to the x sine x. So we now have y times e to the power x is e to the power x sine x plus c, and finally y minus sine x equals ce to the minus x. That brings us to the end of this session. Thank you for listening.